So what I'm going to talk about next is kind of basic data validation and analysis. So the idea here is these are kind of all the things that you'll do with any SAXS data that you collect to make sure that both that it's good quality data and to learn some kind of basic things about it. It's also kind of the category of what we in the community tend to call model independent analysis. So this is things you can learn from your data set without either having to create a model from it or have a model of it, either way. And so these are kind of very useful basic parameters, and there's quite a bit you can learn even before you get into any kind of modeling. So as before, if you have questions, please pop them in the chat and we'll either answer them there or we'll pause and you can ask them and I'll answer them at that point. And we also have a Q&A at the end of this if you want to save questions for them as well. So this is a long talk. I wanted to just provide you with kind of a breakdown of the things that we're going to talk about. So I'm going to start by going back over the scattering profile, talk about what it is, how we generate it, why it's important. Then I'll talk about kind of the various things that can go wrong with your data set and how those manifest in the scattering profile. And then I'll talk about 4 different analysis techniques, the Guinier analysis, molecular weight analysis, Porod and Kratky analysis, and indirect Fourier transforms. Talk about what kind of information those give you, how you do those, and also how problems in your data set will manifest in these different forms of analysis. And we'll kind of wrap everything up. I want to start by looking at the scattering profile, and I'm going to start with some slides I borrowed from Richard a while back, and it's mostly because I'm lazy and I don't want to recreate these, but this is just to remind you of what we're talking about when we talk about scattering. So we start with the scattering from a single molecule. The wavefronts come in, they scatter off of electrons. In particular, we look at the scattering off of pairs of electrons. So again, as Richard said, you can kind of think of these as floats on the ocean. The wave goes by, they bob up and down. They create their own waves in this kind of circular wavefront. And then we look at those waves on a detector. This is a detector, despite the scale of this slide, this is a detector that's sufficiently far away. So we're talking about far field diffraction or scattering. And if you look at just a single molecule, which we can't do in small angle solution scattering, but some of the exfil experiments are starting to approach this. If you look at just a single molecule, you get this speckle pattern on the detector. And this corresponds to the waves coming off of a macromolecule. So more conventionally, we represent these as sinusoidal waves with peaks and valleys, which you can see here. And when they scatter off an electron in the scattering of interest, they change their direction. And we measure them at some point on the detector. And waves from different parts of the molecule will have to travel different distances to reach that point on the detector. That's going to shift this wavefront relative to this other electron pair up here. And so it may shift it in such a way that either the peaks and troughs align or the peaks and peaks align or something in between. So I'm going to get rid of the circular waves now just to make it a little easier to see and add some values here. So you have this incoming in-phase plane wave. You have some path length difference to the detector. And then you have these out-of-phase waves. So if they're completely out of phase, if the peaks of one line up with the troughs of the other, that's called destructive interference, and they cancel out, and you're not going to get any intensity on the detector. If they add, so you have peaks and peaks, that's constructive interference. That's where you get the bright spots. And something between gives you all the dynamic range of the pattern. Now, this is not just for 2 electrons. Of course, we do this over all the electrons in the macromolecule, sum up all of that cancellation in addition, and get out this scattering pattern that we see on the detector. And so this is fundamentally the result of kind of scattered waves off of different portions of a molecule. Now, as it turns out, when we're looking at molecules in solution, we can't look at just a single molecule. The beam is quite large, and so we have a relatively large volume that we're observing and a large number of macromolecules. And because the macromolecules are in solution, not say in a crystal, macromolecules are actually in essentially random orientations. And so what we're observing is not the scattering of a single molecule, it's the scattering of a bunch of molecules at all possible orientations of the molecule. And it turns out, if you work out the mathematics, the scattering from all these molecules in this dilute solution is at all possible orientations, looks the same as the scattering pattern for a single rotationally averaged molecule. And what that does to the scattering pattern we see is it takes that nice speckle pattern that Richard had shown, and I'll show just in the previous slide. It turns this into this halo, the sunrise. And this is really the kind of the information we get out of SAXS is all from this pattern here. One thing I do want to note is that we do lose information, right? Because we have these random orientations, we get this rotational averaging, and that makes quite a few things harder because there's just not as much information because we don't have the scattering of a single molecule, we have the average scattering of that molecule over all its orientations. So that's something to keep in mind. So conventionally these days, and actually for the last, I don't know, 20, 30 years, all scattering patterns have been measured on these two-dimensional detectors. But it turns out there's only one dimension of information in here. If you start at where the beam would intersect the detector, at the beam stop, and you go out some distance on the detector, everything in a constant distance on the detector from the beam stop, and that circle around, should have the same value. And that comes out as a consequence of the mathematics of this rotational averaging. So instead of there being two dimensions of information on our big, nice detector face, there's only one dimension, which is how the intensity varies as a function of distance from where the beam intersects the detector. And so conventionally what we'll do is instead of looking at these 2D patterns, we can reduce it to these one-dimensional, what we call scattering profiles. And so here we're plotting this, intensity as we're going up the detector. And this is essentially, this is intensity as a function of distance on the detector. Now, we don't throw away all the information we get in the 2D detector. Because it's supposed to be the same, what you can do is you can go out to some constant distance, and then you can average all the points at that distance to get your intensity value. And so that improves your signal to noise. So that's the basic processing that goes from these 2D detectors into these one-dimensional profiles. The other thing is that distance on the detector is not really a useful metric. It doesn't allow you to compare between experiments with detectors at different distances from the sample, detectors at experiments at different wavelengths, anything like this. And so you could talk about it in terms of scattering angle, but that's still going to depend on the wavelength. And so what we end up doing is we talk about what we call Q. You might sometimes hear this as S, which is the magnitude of the scattering vector, or the momentum transfer. And this is 4 pi sine theta over lambda. And note that it's proportional to theta for small theta. It's really useful sometimes. And so this is basically a parameter, a way to parameterize the intensity that's independent of the experimental setup. Go to different beam lines, move the detector around, change the energy, even use neutrons instead of X-rays. As long as you put it in terms of Q, at the end of the day, if you measure the same sample and the same conditions at each place, you should get the same intensity versus Q value. More conventionally, we represent this with intensity on the y-axis, Q on the x-axis, I is a function of Q. And this is the scattering profile. This is kind of the single fundamental piece of information that we get out of SAXS experiments. So Richard put up a more complete version of this equation earlier, but I want to point out some kind of key dependencies in the intensity of the scattering profile. So we have this factor out front, which is independent of where you're looking on the detector. And this is essentially a scaling factor. And so the scaling depends on, there's some constants about your beam and about the X-ray matter interaction. But then, leaving those aside, you get the molecular weight, you get the concentration, and you get this rho difference here, rho 1 minus rho 2. And this rho is the scattering density, the electrons per unit volume of your protein and your solvent. And so the difference between the scattering density of the protein and the solvent squared shows up in this islet Q. And this is why, for example, Kushal was recommending to avoid things like sucrose or high concentrations of salt. So that increases the electron density of the solvent. It reduces this contrast term, and that reduces the intensity you get, holding everything else equal in the experiments. And so you can actually utilize this in many ways to do interesting experiments. Most of those show up in small angular neutron scattering, and you'll hear about that on Thursday. But for our experiments, we generally want to try to maximize this difference so we get the best signal, which means, keeping modest salt concentrations and avoiding other additives unless necessary. So there's the scaling factor. Then there's two terms out here. There's this form factor. Sometimes you see this as just f of q, sometimes you see it as the squared modulus. This contains the shape information of the macromolecule. This is usually what we're interested in. So this is what causes the scattering profile to change as a function of Q, which is why we can get out information about the shape. We look at how it varies, and that tells us what this form factor is doing. There's also this S of Q term. It's called the structure factor, and this relates to intermolecular interactions. If you want to learn about the shape of the macromolecule, you want this to be 1, because otherwise you're going to get variation in the scattering profile as a function of Q that doesn't correspond to the shape. It corresponds to the structure factor, and that's going to lead you astray when you're trying to interpret shape information. So what we end up having then is we have this S of Q. If you have a dilute solution where you've added, salt or something to screen for interactions, this typically becomes constant and uniform, and we can make that assumption in our analysis. You can, as Richard mentioned earlier, actually study the information out of this interactions by looking at the structure factor term, but that's not as typical, and it's not something we're really going to cover in this course. I just like to mention that it's there. So this is a slide I showed you earlier. This is, again, back to the typical SAXS experiment. We have an X-ray source, creates an X-ray beam, it shines on the sample. We measure the scattering on our detector. Again, we have to measure the proteins in solution and then the solution by itself. We subtract off this background scattering or this buffer scattering to get the scattering of just the protein by itself. So this is our basic procedure. To go through kind of the reduction steps, so we collect the data as 2D images. These 2D images are radially averaged into one-dimensional scattering profiles, I of Q. Generally speaking, and I'll go over the reason for this in a few slides, we collect multiple profiles of both the sample and the buffer. And this is because we're looking for radiation damage. You want to see if there's any change with exposure. So you want to be able to exclude that. So we collect multiple profiles of each. We average all of the useful buffer and all the useful sample profiles. Then we subtract the buffer from the sample to create a subtracted scattering profile. And this subtracted scattering profile is basically, it's the basic data form in SAXS. It's what you base all the rest of your analysis on. One of these, or if you have multiple systems or multiple conditions, multiple of these. And that's where we're going to do all the rest of our analysis. The next thing that I want to say is a little bit more about what this scattering profile actually is. So just to kind of summarize the previous slides, right, we call it I of Q or I of S sometimes. It exists in reciprocal space. So this means the Q value has units of 1 over distance, usually 1 over angstroms or 1 over nanometers. And this is kind of an unusual thing for people who haven't thought about scattering before. But what it basically means is that where things show up is reversed. So big things, because we're in 1 over distance space, big things show up at more at low Q. And small things show up more at high Q, right? Because you take 1 over something big and it's small, 1 over something small, it's big. And so on a practical sense, what this means is that the low Q region of the curve contains information kind of on the overall size and shape of the macromolecule. Then the mid to high Q region contains information about finer structure, tertiary structure, secondary structure, things like this. And so it's useful to think about stuff on the left at the low Q near the beam stop, that's the big stuff, and going out is more of the shape. The scattering profile itself, as I mentioned, represents the scattering from the rotationally averaged macromolecule in solution, so we've lost information. That is an important point, and that'll show up again as we talk about more advanced analysis and how we deal with some of that, some of the limitations. And then the Q dependence in the scattering profile comes from the molecular shape and the molecular interactions. So if you want to learn about the shape, it's important to eliminate the interactions. And to verify that these interactions have been eliminated, this is why we've been saying, especially if you're doing batch mode, you need to do a concentration series to look at several different concentrations and make sure you're not seeing that effect in your profile. In SAXS, I find that typically there's enough of a concentration gradient across the peak that you can see if you're seeing any intermolecular interactions, and you typically only need to run it at 1 concentration unless there's something particular you're looking for. So a couple notes just about plotting the scattering profile. So this is the same scattering profile represented on 3 different types of plots. So here we have linear axes, here we have a log y and a linear x, here we have a log y and a log x. And as you can see, it actually looks pretty different on these 3 plots. Typically speaking, unless there's something in particular you're looking for, we don't represent data on linear plots. And the reason is you can look at this log scale axis here, see that we're covering kind of 3 or even 4 orders of magnitude in intensity over the course of the profile. So if you put it on a linear axis, you hide a lot of significant features, particularly in the mid to high Q region. It's best practice when you're presenting kind of general SAXS data to do it usually as a log-lin, maybe as a log-log. The difference here is that the log-lin emphasizes the kind of mid to high Q, which is the shape, whereas the log-log emphasizes the low Q, which is the size. So the choice of those depends on what you're looking at. But this is just kind of a housekeeping note. You're almost always going to see profiles. If they're not for some type of analysis, you're going to see them on either log-lin or log-log plots. All right, what I'll do next is go on to talking about what can go wrong with your data and how you see that in the profile, but I'll take a brief moment to see if anybody has any questions. There are a number of things that can go wrong with your data, and it's important to be able to recognize what those are and how they show up in the profile so that you avoid analyzing something that isn't what you think it is. The first of these is kind of a catch-all, and I'm going to call it poor quality sample. So this feeds into what Kushal was talking about in his talk. Knowing and assuring that you have good sample going into the X-ray beam is very important. If you have aggregates or unexpected oligomers in solution, that will throw off your analysis in ways that I'll show in the next slide. This poor quality sample, though, could also be, for example, if your oligomeric state doesn't match expectations. It's not necessarily bad, but it means if you're trying to do analysis for, say, a monomer when you have a dimer, you're going to get the wrong results. And if you're not careful, you'll end up with something that's completely wild. So you need to be sure that you understand what's going on in the solution. Similarly, maybe you're trying to form a complex and it doesn't form or doesn't form completely. So really understanding what's in the solution is essential for getting the most out of your scattering data and not fooling yourself with kind of what else is going on. So that's one thing that can go wrong. The next thing is radiation damage. So as we've mentioned several times, right, the X-rays can cause damage to the proteins, and this will usually manifest as, or always manifest as, unexpected time-dependent changes in the measured profile. So if you're expecting everything to stay the same, and you see it changing as you expose it, that's usually a very good signature for radiation damage. Typically, radiation damage manifests as aggregation. For example, you reduce cysteines and form disulfide bonds, cross-links between molecules or something like that. But it can also, I've seen complexes fall apart and see buffer damage. There's a variety of different ways it can show up. But looking for these unexpected time-dependent changes and making sure that you're excluding them from your analysis or remeasuring the experiment if necessary without it is important. You have concentration effects. So this is most of the structure factor that I was telling you about. So this is concentration-dependent changes in the measured profile. This can look like an upturn or a downturn at low Q. Usually it's a downturn indicative of repulsion. And then the final kind of thing that can go wrong with your data is you can have bad buffer subtraction. So this could be a bad buffer match if you made the buffer up by hand instead of, say, doing a dialysis step or something. Could be capillary fouling. Maybe you've damaged something that's stuck to the capillary between your buffer measurement and the sample measurement you're using, so the background is no longer the same. And this will usually manifest as the profile going negative at high Q or low Q, which is an oversubtraction, or the profile being offset at high Q or having uptick at low Q, which is an oversubtraction. So what do these actually look like when it comes to profiles? What I'm showing here is a plot of the profile for the same macromolecule, but I'm showing it for both an unaggregated and an aggregated version. And so you can see there's this distinct change at low Q. Corresponds to this kind of uptick at low Q, as we sometimes call it. And this is a very clear signature of an aggregate or of multiple sizes of samples in solution, even if it's not non-specific aggregate, perhaps multiple oligomers. And the basic idea here is big stuff scatters more at low Q, so you're going to see these kind of overall size-dependent changes show up more here. It's also related to the Guinier range, which we'll talk about in a few slides. So I'm actually looking at the chat now. I have that up. So you can see there's a question. Is this a lin-lin or log-log on the plot? So this is a log scale. You can see the ticks, if you can read the tick marks, are in decades. 10 to the minus 4, minus 3, minus 2, minus 1, minus 2, minus 1 here. So this is the log-log plot. That's a good question. I'm showing this to emphasize the change at low Q, which is why I use a log. So radiation damage, you actually usually see it as aggregation, so it looks similar. But in this case, this is a set of exposures. We did, I think, 10 exposures. You can see the first one here at the bottom, then the next one in the middle of the exposure set, and one at the end. So you can see this time-dependent change in your profile. And this, especially showing up as this uptick at low Q, is very indicative of radiation damage to your sample. So this is another way of seeing that same kind of damage, but manifesting rather not from poor sample prep, or maybe not poor sample prep, but just samples that aren't behaving as you expect, but manifesting from the beam itself, from the probe that we're using to study the sample. This is what interparticle interaction typically looks like in your samples. So here we have the same sample with multiple different concentrations. And you can see as I increase the concentration, the profile goes down at low Q. This is very indicative of structure factor effects of these repulsive interactions. And this is a slide I borrowed from Tom Grant. You can kind of see this here where you have the overall form factor, the shape, and then you have this structure factor term that's either attractive or more typically repulsive. And then when you multiply those two together, you get the overall Q dependence of the scattering profile, and that leads to this either uptick or downturn. There's also more subtle changes in the region out here. And so this is the kind of thing that you'll see there. So there's another question in the chat. Do these slight changes in scattering profiles affect the end structure or map obtained? Yes. Any change in your scattering profile will end up affecting what's being obtained from the analysis. Changes like this, I would not call slight. These are very significant changes. You know, keep in mind this is a log plot, so this is probably changing by a factor of 2 out here in the intensity at low angle. So these are very large changes, but even small changes will affect the results of your analysis. So you want to be very careful with this kind of thing. And we'll show you how to be very careful in the rest of this talk. Analysis techniques you can use to make sure it all looks good. Here we're looking at what subtraction errors might look like. So this is an artificial error. I just took a profile and the buffer subtraction, or rather the buffer profile and the unsubtracted profile. And I artificially scaled the buffer by 3% in either direction. And so if you scale the buffer too high, you can see that get this kind of downturn here and a drop at the high Q. It's over subtracted. If you scale it too low, you get this kind of raised bit at high Q and this uptick. So these are signs. You might not see all of these. It depends on how you've messed up your buffer, where it's going to change, but usually one of these will show up as a buffer subtraction issue. And this is why it's so important. Even a few percent change in the buffer will lead to significant errors in your scattering profile and throw off all the rest of the analysis. So what I want to emphasize here is just kind of in summary, SAXS is what we call low information content measurement. If you work out the math, you can make some claims about like Shannon channels and entropy and things like this and information theory. We don't go into that in this workshop. There's plenty of papers if you're interested. But at the end of the day, there's something like 5 to 10 independent data points in a scattering profile. We massively oversample, but there's only 5 to 10 independent parameters basically that you can extract or fit to a profile with a given type of analysis. So you don't have a lot of information there in the first place. And then the challenge is that even bad SAXS samples, even samples where something's gone wrong, will provide signal. And so this is unlike, say, in crystallography, where if you get bad crystals, they just don't diffract. Here, if you get something with some aggregate in it or something with a bad buffer match, you're still going to get a result. And so this is why, because you always get this result, and because it's easy to overfit the data, validating that you've measured good data is extremely important. And so the basic analysis methods for SAXS that I'm going to go through in the rest of this talk, they both verify that the data quality is good and they provide you useful information on the system. And so these are important things to do every time you're collecting SAXS data, every time you have a new system, every time you have a new measurement. Check these and you make sure it all looks good. So what I'm going to do next is talk about Guinier analysis, but I can pause for a moment if there are any other questions on so far how things can go wrong. So there's a question in the chat: can you overcome radiation damage by just using more intense X-rays with faster flow rates? You have it half right. So radiation damage depends on essentially on the flux density of the beam. And as the flux density increases, so too does the probability of radiation damage. So if you're seeing radiation damage, the solution is to attenuate usually, or add in things that prevent the damage. You can also flow your sample faster, though in the case of, say, a size exclusion experiment, you're limited by the flow rate of the column. And so that's usually a fixed factor, at least in those experiments. So what you end up doing in practice is attenuating the signal in some way. There are some other ways to get around this. Additives are the most common one. You can use a coflow sheath cell like we do that helps reduce the damage. But at the end of the day, if nothing else is working, you just throw away some of the beam. Is the low Q profile mostly useful to verify the sample quality? No, or maybe yes. You can get other information out of it. You can get size and molecular weight information. But at the same time, I would say its most useful quality, if not mostly used for, is verifying the sample quality itself. And that actually leads me very nicely into Guinier analysis. So I think I will start on that part of the talk. So Guinier analysis, which is named after Andre Guinier, is a way of looking at the scattering profile, particularly the low Q region of the scattering profile, and fitting it to a particular shape to extract out information. And so the insight that Andre Guinier came up with is that for homogeneous monodisperse solution of macromolecules, or I think really anything, as the Q vector, as this Q goes to 0, you can always approximate the intensity as some overall scaling factor times e to the negative Q squared Rg squared over 3, where Rg is the radius of gyration, which is related to the size of the macromolecule. And this overall scaling factor we call I of 0, because if you put Q of 0 here, this exponential goes to 1. And so this is the scattering at 0 angle. And if you think back a few slides to when I showed you the scaling factors of the scattering profile, this scattering at 0 angle is related to the molecular weight times the concentration. And so you can actually use it to get out molecular weight information. So the Guinier analysis itself allows you to get out information about the size and information about the molecular weight. So I find it's nice to illustrate this is only true at certain Q values, when Q is small enough. And you can see this very clearly on this plot here. So here I've taken the log of the intensity and plotted it versus Q squared. And you can look at this equation, right? If I were to take the log, and it becomes log of I of 0 plus, or rather minus Q squared Rg squared over 3. So if I then plot versus Q squared, the Guinier region becomes linear, and anything outside the Guinier region is not. And so you can see we have this very clear and nice linear region of the scattering profile, where this Guinier approximation holds true. And then you have a region where that approximation is not true. And so we can fit this linear region to this approximation and get out these parameters. In particular, if we fit the line itself, the slope is negative Rg squared over 3, and the intercept is the log of the I of 0. And so this is the basic idea behind Guinier analysis, is we can fit this region where the approximation is true and get out these two parameters of interest. So a little bit more about the radius of gyration. Vishal mentioned this in his talk a bit as well, but it is the RMS distance from the center of mass. That's the technical definition. And there's some definitions here that may be useful. I've only put them for your reference. I'm not going to go through it, but there are some mathematical definitions that could be useful for you. The thing I want to emphasize, and this is a figure I borrowed from Vishal, is that there's various different radii you may hear people refer to, and they're not the same, right? The Rg is not the same as the hydrodynamic radius, is not the same as the hard sphere radius you get by rotating the macromolecule, etc. And the ratio of these actually depends on the shape of the macromolecule. It's not always going to be the Rg is the smallest, and theoretically, at least, the ratio of Rg and Rh can give you information about the shape of the macromolecule, though most people don't usually try to extract it that way. But it's useful to remember these aren't all the same, so you need to make sure you're comparing apples to apples if you're looking at different sizes for the macromolecule. So digging a bit more into the Guinier analysis, I said that this analysis is only accurate at low Q, and that you have to fit a region in which the analysis is, which the approximation holds, in which the analysis is valid. And so the big question, and actually the big challenge for Guinier analysis, is how do you pick the fit endpoints? How do you pick the region in which you're applying this approximation? And it turns out it depends on the particle shape and size. More than Q being small, the criteria that we place for this approximation to hold, so we need this exponential to be small, which means we need Q times RG to be small. And so what I've plotted over here, this is a plot of the intensity on a log scale versus Q times RG squared. So that's this essentially exponential term. And so here, the black line is what the Guinier approximation looks like. It's a line like you'd expect on this plot. And then I have plots for various geometric shapes: a sphere, which is the one down here, a thin rod, which is the one up here, and a thin disk, which is this one that diverges much later. And so you can see that these are all actually objects with the same, we've taken out the size. Even once you take out the size factor, the shape of the object determines how far this Guinier approximation holds, right? The line for the thin rod starts diverging from this linear line, black line here, much earlier than the line for a sphere or the line for a thin disk. And so the range of validity of this approximation depends not just on the size, because you need the QRG factor, but also on the shape. And this is very important because it helps us pick the endpoints. Conventionally, what we do, there's always a trade-off here between using enough of the data range that you get a good fit because you have enough data points, and not using so much of the data range that you get a bad fit because the approximation is starting to break down. And the community as a whole has decided that for spherical objects, essentially globular macromolecules, or disks, you usually fit to a QRG of 1.3. Rods, thin rods that diverge much earlier, you fit to a Q times RG of about 1. The early side of the fit, you should always extend the Guinier fit to as low a Q value as you can, as you've measured. The earliest data points, the first 2 or 3, maybe 5 data points in the data set, can often be quite noisy because there's only a few pixels on your detector in those Q points. But if you have to exclude more than 3 or 5, and ideally you exclude none, but if you have to exclude more than 3 to 5 points at the start, that really means that your data might be bad. So you want to be careful with this, and I'll talk more about that in the next few slides. For this minimum value, in order to say we have a large enough Q range, for a globular molecule, we usually say you need Q min times RG to be at least less than 1, preferably less than about 0.65. For a rod, of course, it needs to be less than that. We don't really have fixed cutoffs, but 0.65 is probably another reasonable one as well. So that's kind of the criteria for the fit, but those of you kind of paying very close attention may have realized an issue with what I've said, which is that the range of the fit, right, these Q limits depend on a factor we're deriving from the fit itself, the radius of gyration, right? So the question is, how do you pick a good maximum Q value and minimum Q value before you know what the radius of gyration is? So you have this kind of circular problem where you need a factor from the fit to get the result of the fit itself. And the answer is that we do this in an iterative fashion. So we'll start out by just kind of guessing a starting maximum Q value for the fit. Maybe you have some idea what the size of the macromolecule is. Maybe you've looked at the plot and seen where the linear range is. Maybe you're just picking something out of thin air. You then calculate the Guinier fit for the range that you've selected. You get out the RG value. You look at whether the maximum Q of your fit times the RG is more than 1.3. If it is, you reduce the maximum Q. If it isn't, you increase the maximum Q. And you repeat these 2 steps here, recalculating that fit, changing the Q value, until you converge on a final maximum Q. And we'll have a chance to do this actually in the tutorials in the hands-on portion tomorrow. I should point out these days software does most of the work for you. It'll come up with an initial Guinier range, and then you usually just have to refine it by a few points to get a good result. The minimum Q should usually be the lowest available Q point. And there are some criteria we look at for a good fit. So the first of these is you want enough fit range. So Q min and RG ideally less than 0.65, fitting to your lowest Q point. Qmax Rg is about 1.3 for something that's globular or a disk. Qmax Rg about 1 for something that's extended. One of the key points actually is looking at the fit residuals. So what a fit residual is, it's the difference between the line of the fit and the data point at that position. And so that difference can be plotted, and the residuals for a good fit should be flat, which is to say no shape, not curving in any way, and they should be randomly distributed about 0, because what you're saying is you fit the data as well as you can within the noise of the data, which is just popping these data points off the line and up or down about 0. And so this fit residual is a very important way for judging fit quality. And then, of course, you want the fit to extend to as low Q as you can. So these are kind of our criteria. One thing that's often a little bit puzzling for people is how do you pick whether you want to use 1.3 or 1.0 or something else, especially if you don't know initially what the shape of your macromolecule is. And the answer is what you should do is you should start with 1.3. And then if you see non-flat residuals, bring that maximum Q down, reduce it until you get to 1.0. And if that's leveled out your residuals, then you have a good Guinier fit, and that's telling you have a shape such that 1.3 is not an appropriate endpoint. It's actually giving you some information about that overall shape. If you still have some weirdness in your residuals, then you probably have a problem with your data. And so that is actually why we do the Guinier analysis. You get out this RG, you get out this I0, but perhaps even more so, or at least equally important, is that most of the problems that I just showed you with your data show up at low Q, which means they're going to show up when you try to do the Guinier fit. And in particular, nonlinearities in your Guinier analysis, these are indicative of problems with your sample, right? Aggregation causes a characteristic upturn at low Q. This could be caused by aggregates in the sample or by radiation-induced aggregation. And you can see here, here's a nice Guinier region with no aggregation, nice linear fit. Here's a lot of aggregation. You can see there's really no linear range. We try to do this fit. And here's a sample with a small amount of aggregation. You can see there's just a little bit of deviation at the low Q, and it otherwise fits relatively well. And so doing the Guinier fit and seeing how well it agrees with what we expect with this approximation is a very good way at seeing what's influencing low Q. Downturns at low Q, this is not a Guinier plot, this is just to remind you, downturns at low Q are characteristic of the structure factor. These also show up in Guinier fit. And so not only the shape of the fit compared to the fit line, but the shape of the fit residuals can also help you see the problem. So here we have a monodispersed sample. We fit it to the Guinier fit, it fits quite well. The residuals are flat and randomly distributed. This is what we want to see. Here we have a sample with aggregation in it. You can see we have this uptick at low Q, and even if I've cut off most of that, we still have this kind of trend in the residuals. It's especially elevated over here and a little bit over here, and it's a little below the 0 line in the center. This kind of upturn or smile in the residuals, as we sometimes refer to it, is very indicative of aggregates in your sample. And I should say when I say aggregates here, it could be non-specific aggregation, or it could be, multiple oligomers existing in solution. It's indicative of the presence of larger species in solution. So this is one thing to keep an eye on. You can also see the same kind of thing when you have a repulsive structure factor interaction. So here we have this obvious downturn, and you can see a similar kind of downturn, or sometimes called a frown in the fit residual, where it's below the line at the ends and above in the center. So this is very indicative of these repulsive structure factor interactions. This is a very extreme example, but this is the kind of thing that you'll see. So to summarize on the Guinier analysis is sensitive to low Q. Most of the problems with your data will show up here. You get aggregation, you get radiation damage, you get interparticle interactions, and some buffer subtraction issues will also show up here. The Guinier region should be linear. You should get flat fit residuals. There should be an upturn in the profile of the residuals. If you see that, that's aggregation usually. If there's a downturn in the profile of residuals, that's usually a repulsion. And either of these indicates an issue with your sample that you need to evaluate before continuing analysis and possibly remeasure. You also get the RG, which informs on the particle size, and you get out the IF0 value, which informs on the particle mass. And I'll tell you how to use it to get particle mass actually in the next section of this talk on molecular weight analysis. But again, this is a good point to pause and see if there's any questions so far about Guinier analysis. All right, so we'll continue on. There's, again, Q&A at the end of this talk, so we'll take questions there as well. So what I'm going to talk about next is how you get molecular weight from SAXS. And so the first thing I want to throw out there is just that molecular weight estimates from small angle X-ray scattering or small angle neutron scattering are really kind of maybe 10% accurate at best. You don't want to rely on SAXS to determine the molecular weight of the system. You should use another approach, moles, AUC, mass spec, something like that. Instead, what you want to do is you want to use the SAXS molecular weight to verify the state of the macromolecule in solution. Is it in the oligomeric state that you expect? Is the sample intact, or has it, degraded during transport and measurement? Are you getting the complex forms that you think you're getting? It's really important to verify that what's in solution is what you're expecting, and the molecular weight you calculate from SAXS is a good way to do that. So I'm going to tell you about 6 different methods for calculating molecular weight. The reason there are so many is that they're useful when you have different information or in different circumstances. 2 of them are concentration-dependent methods. These are not useful for SAXS. In SAXS, because there's dilution on the column and dilution even between the UV cell and the measurement, generally speaking, we don't have a precise enough metric for the concentration over the elution to use the concentration-dependent methods. So people have developed these concentration-independent methods that are useful for SAXS data, as well as batch mode data. So we'll talk about all of these. So the first 2 methods I want to talk about rely on knowing the concentration of the sample. These are the concentration-dependent methods. And there's really 2 approaches here. So the first of these is that when you measure SAXS data, you can measure it either on an arbitrary scale, which is to say there's just an arbitrary scale factor on your intensity, or if you've calibrated the instrument, or your beamline scientist has calibrated the instrument, you can measure it on what's called an absolute scale. Usually this has units of 1 over centimeters, but you can see other units show up. So properly calibrated intensity using a known standard. Once you have this I of 0 in absolute units, the molecular weight can be calculated by this formula, where you have the concentration, you have the scattering contrast, which you can calculate from your buffer or use just kind of a generic factor for, and you have, of course, just alphabetical numbers. So this pulls out the molecular weight. And so this can be quite useful, but it's only as good as knowing the concentration, knowing the scattering contrasts. And so you can introduce, and of course, as good as your I of 0 value. So you can introduce significant errors if you don't have a good concentration measurement, which is why Kushal spent so much time talking about why you need to measure concentration well and different ways you can do it. So this is one approach. Even if you don't have the intensity in absolute units, you can measure a known standard on the beamline, like lysozyme or glucose isomerase, something that's very well behaved and monodisperse and has a known molecular weight. And then if you take the ratio of the I of 0 over the concentration for your unknown protein and your standard protein, you can calculate the molecular weight of your unknown protein in this fashion. And this is actually simply derived if you take the ratio of this equation here, you can solve for one of the molecular weights and you end up with this equation. And it holds even if they're not on the absolute scale. Caveat here, again, you need to know both concentrations very well. And you need good I0 values. And the contrast has to be roughly the same between the standard and the protein you're measuring. So if they're in very different buffers, this measurement will not work. So these are the concentration-dependent approaches. And yeah, just to emphasize, if I haven't said that enough, they both require accurate concentration measurements. So now I want to switch over to the concentration-independent methods. So there's 6 or 4 of these, 6 total methods, 4 of these that I'm going to highlight. The first, there's actually multiple methods, but I'm kind of grouping them all into one. They're what are called Porod volume methods. It turns out that, of course, right, mass can be calculated as density times the volume of the particle. And you can calculate what's called the Porod volume, which is the volume of the particle in solution, using this equation here. You can then use a density. Often people take the average protein density, but you can use something else. You multiply it by the volume and you get out a molecular weight. The challenge with this approach is that this integral itself can be quite hard to calculate accurately. So as you get out to higher Q, your data tends to be noisier. We never measure out to infinity, of course, because we haven't found a funding agency that will buy us an infinite detector yet. And so all of these things put together mean that this can be a not very accurate number. There's also some other influences. So people have developed various advanced techniques based on this idea that allow you to truncate this integral and only use a certain amount of your data set, and then compensate for that missing data and come out with a more accurate number. And the version that we're going to use is based on this reference here, and we'll go over that in a little more detail in the tutorial tomorrow. Actually, I have a chance to use it. The volume of correlation method is a more empirical approach. So here they came up with this VC quantity, which is I of 0 over, again, another integral. So it's very similar to this approach in that regard. You then take the ratio of that with the RG, and then there's some empirical coefficients that they calculated out. This 1 over K and the C, which is not concentration. This is what they used for it. And these have values for proteins and RNAs, and you can use that to calculate out the molecular weight. So this is another approach. There's two others that I want to highlight. The next one is actually a machine learning method. So this is a kind of nifty approach that came out a few years ago, where they basically took all the structures that were available in the PDB at the time. They calculated out the SAXS profiles for those structures, and then basically scaled out the size from those. And you compare your scattering profile to this family of structures, of scattering profiles from structures. You find the one that's kind of most similar, and then you use the scaling, like from the RG value and the I of 0, to add in an overall size factor, and you can calculate out the molecular weight based on saying, okay, I know it's kind of rod-like with an RG of 20 or something like that. And it actually ends up being quite accurate in some cases, typically when your sample is quite rigid. So that's a kind of fun, newish method. And then this last method I want to highlight is one that takes the three other concentration-independent methods and kind of combines them. This is a Bayesian inference method, and it takes the Porod volume, the volume of correlation, and this comparison to known structures, and again calculates them all for a large set of theoretical scattering profiles from the PDB. And then from the PDB, you know what the actual molecular weight is. You know what each of these other methods is yielding. And so you can say, okay, given that I know that my molecular weight's 25 and the other methods are yielding 20 and 30 and 22, how do I combine these? What's the right weighting, or what's the right probability of using these other methods to give me the actual molecular weight of my sample? And so they do this for a large data set. They come out with this essentially set of weighting coefficients that lets you combine these other methods in a way that in theory minimizes the weak points and gives you the best molecular weight every time. It's not always true, but it's often true. These four methods don't rely on the concentration of the sample, which makes them useful as checks on methods 1 and 2, and also in cases where the concentration may not be known, such as SAXS.
So this is a question in chat that's probably worth having a discussion. Are you expected to get approximately the same molecular weight using these different methods?
So that leads into my next slide, actually, honestly. So the answer is no, not necessarily. So each of the methods fails in different ways. So the absolute scaling method requires having an accurate calculation of macromolecular contrast, partial specific volume. It depends on an accurate concentration measurement and an accurate scale calibration, absolute scale calibration. The reference to known standard provides kind of you need the reference standard and a similar buffer. You need an accurate concentration for both the reference and your sample. The Porod volume method works best for compact globular rigid macromolecules, requires accurately known molecular density. The volume of correlation will fail for protein nucleic acid complexes. You need the integral to converge. It's sensitive to noisy high-Q data. It fails for molecules that are too small, just because they didn't include those in their fit set for the coefficients, I think. This tends to work best for flexible systems to volume of correlation. The comparison to known structures only works for proteins. It doesn't work for flexible systems. And the Bayesian inference only works for proteins. In theory, it minimizes these other issues, but if one of these is bad enough, it can throw off the Bayesian inference and you'll get the better value from one of these individual approaches. So everything else being equal, ideally, all of them would give you the same approach. But in reality, they all have different failure modes. They all work best for different types of systems. The other thing I want to point out is that all the methods will fail if your Guinier fit is bad, because they all rely on either I0, RG, or both. So if you have a bad Guinier region or you've done a bad fit, you're not going to get reliable results out of the molecular weight. The integral methods are also sensitive to accurate background subtraction. So when you're calculating molecular weight from SAXS, you need to be really aware of the failure modes. And you should think ideally ahead of time, okay, this system is flexible, so maybe I want to look at the volume correlation. Or I know this one's pretty rigid, so probably the Porod volume is going to give me the best results. And then you should use the methods that work best for your data, not the ones that best match your expectations. You always want to be verifying that the molecular weight matches your logarithmic state. And if it doesn't match your expected logarithmic state, don't assume that you know what's going on. It could be an error in the molecular weight calculation from SAXS, or it could be a sample problem. And here's where having a complementary method, moles, AUC, something like that, is going to be really powerful for you. And this is why we do SAXS in line with moles, is we get this highly accurate molecular weight, which can resolve a lot of these ambiguities around SAXS data molecular weight. So hopefully that sufficiently answers the question. There's also a bit more of this in this tutorial. So I have a couple more things to talk about, but I can pause here for more questions if we have them. So what I want to talk about next is kind of two bits of analysis that are related. We have the Porod and the Kratky analysis. The Porod analysis is what I'm going to start with. And the basic idea here, Porod derived this property that objects with sharp boundaries, like an ideal sphere, and no internal structure, have scattering that follows what's called Porod's law at wide angles. The classic statement of this was I of Q is proportional to Q to the negative 4 at sufficiently large angle, and Q times the size of the object is large. And you can see that manifested here in this plot. Here I'm plotting the scattering for spheres with two different radii, 15 and 150 angstrom. And they have the same overall shapes, but they're shifted on the plot. But this decay at high Q, this overall envelope, this dashed line here, has the same slope in each case, and that slope is -4. And so the slope of the decay, regardless of this internal structure, is what we're looking at when we're talking about Porod's law. More generally, as it's usually stated, I of Q is proportional to Q to the negative D, where D is what we call the Porod exponent. And that can have values from -4 to -1, depending on the shape of the particle. A rod goes as Q to the -3, a disk goes as Q to the -2. Unfolded or random walk polymers, so IDPs, often go around Q to the -2 as well. Fully extended polymers in solution will go as Q to the -1. And so this can be a useful parameter to think about. I will say that you often see this in material scattering, interpreted in terms of particle size, shape, and porosity. We don't usually do that in SAXS. And part of that is because of the way the law breaks down at higher Q due to kind of internal shape and hydration effects. Makes it hard sometimes to fit accurately and get a good Porod exponent. And so instead of doing Porod analysis, we take advantage of this overall decay and use it in a more graphical analysis that we call Kratky analysis. So here, as I said on the previous slide, unfolded proteins have Porod exponents near 2. And folded generally have exponents near 4 if they're globular. So a Kratky plot is where you take Q squared times I of Q versus Q. And so if you have something that's well folded, it's going to come up a bit. This part of this is the Guinier range, which is exponential, right? And then it'll come back down pretty quickly because Q squared times Q to the negative 4 is still Q to the negative 2, and that's fast decay. On the other hand, if you have something that's unfolded, Q squared times Q to the negative 2 is constant. So you're going to have it come up and you're going to have it level out in this plateau. Something that's partially unfolded or has flexibility but isn't completely unfolded, it's going to do something in between. And it's not on this plot, so I always include this little extra bit. If you have something that's really extended in solution, it's going to come up and just keep going up like this. Now, there is an issue with the kind of classic Kratky plot. And the issue is that Kratky plot depends on the size of the object and the scaling of the scattering profiles. So here on the left, I'm plotting glucose isomerase and lysozyme, which are both quite compact globular objects, very similar in shape. But the Kratky profiles here look very different because they're very different sizes and at different concentrations. And so what we can do is we can actually kind of collapse this information, remove out the size and the scaling by normalizing by the radius of gyration in I of 0. And so we create what we call a dimensionless Kratky plot, which is plotted as QRG squared times I of Q over I of 0 versus QRG. This removes out the size effects, the concentration effects, anything like that. And so things that are the same shape, like glucose isomerase and lysozyme, look the same on a dimensionless Kratky plot. And you can see that here, the blue and the red curves essentially overlay. So more generally speaking, globular particles on this dimensionless Kratky plot all have the same shape. And so deviations from that shape inform on flexibility and extendedness. So something globular is going to come up, it's going to come back down, it's going to be this relatively symmetric shape. It's going to come down near 4 in the QRG, it's going to peak at 1.1, and the peak position is going to be QRG of root 3, which is about 1.73. You can actually derive these parameters. These are nominally exact values for a sphere. So this shape then, if your peak is moving up and to the right, or if this tail is coming up, indicates flexibility and disorder, or extendedness, I should say. Something completely unfolded is going to come up and level out between 1 and 2. Ideal random chains are 2. Disordered things are between 1 and 2 usually. And so you can use this to interpret rather in a kind of a semi-quantitative way. You can't put an exact number on it, but you can say, look, this is definitely more flexible and more extended. I'll talk more about how to do that in the talk on Friday when I go over kind of more analysis for extended systems. How would the Kratky plot look for non-globular proteins? Well, something that's unfolded, it would look like this. For something that's partially unfolded, look like this. This is also kind of what an extended thing might look like, or rather something more rod-like might look kind of like this. They'll be in between the two. And again, we'll talk more about this on Friday. But it's a good question. Interpreting this is a little bit of an art sometimes because there isn't a quantitative number you can put on it. So the Kratky analysis itself, the Kratky plot informs on the flexibility and shape. It's relatively insensitive to small amounts of aggregates or radiation damage, but the dimensionless Kratky plot depends on the RG and I0 from Guinier, so it's very sensitive to these things. Kratky plots are extremely sensitive to buffer subtraction issues, and the dimensionless Kratky plot will provide you this kind of semi-quantitative assessment of flexibility and shape. So the final thing that I want to go over is indirect Fourier transforms. So the basic idea is the scattering profile, as I said before, is in reciprocal space. It's in this 1/, distance space. And those of you who have done the mathematics, taken a few physics classes or chemistry or something, you may recognize that the Fourier transform is a mathematical technique that allows you to basically go between what are called conjugate spaces, in this case, the space of 1/, distance and the space of distance. So we can take our scattering profile, we can apply this mathematical tool to it, and we can get out information about our macromolecule in real space, not just in this reciprocal space. And so I'm showing you the equations here. We'll go over in more detail what these do and what the P of R function means, but essentially you can go either way. You can go from the P of R function, transform it back to this I of Q, or you can go from I of Q and transform it back to P of R. And you may see these sometimes with factors of 2 and pi in different places. Depends on people's preferences, but these are the basic equations, and this is how it might look. You go from this data here, you transform it into this P of R function, and then you can transform that P of R function back into this black line, which is the kind of smooth fit to the data. So what I'm going to start by talking about is what the P of R function is and why it's useful, and then I'll tell you how to get it, how to actually do the transform. So this is again an image I borrowed from Richard. The P of R function is the histogram of all possible pairs of electrons. We call it the pair distance distribution function. And so it really is as straightforward as the name makes it sound. Basically, you look at each pair of electrons in a macromolecule, represented here in some blue lines, and you see how far apart they are. And then you just histogram those distances. You say, okay, how many electrons are 10 angstroms apart and 20 angstroms apart? and etc. And you create this plot of distances, number of distances versus the distance, this pair distance distribution function. And so the shape of this, of course, depends on the shape of the macromolecule. We'll talk about that more in the next few slides. But one of the obvious features is that it tails off out here to 0. This represents the maximum dimension of the object. This is the dimension at which there are no more electron pairs in your object. The shape effects here, you can get a shoulder that's, for example, because there are kind of 2 domains in this macromolecule. And so you can learn a lot by looking at this P of R function. The way that we usually start interpreting it is in terms of geometric shapes. This will give you an idea of what's going on. What I have here is I have a set of lines corresponding to the P of R function for geometric shapes with the same maximum dimension of 100 angstroms. And so a solid sphere is represented by this red line here. It comes up, it comes back down. It's quite symmetric and almost Gaussian in shape. So this would be what a globular protein would mostly look like. Something that's more extended, this longer thin rod. You can see it has this distinct peak here at low distances, which corresponds to all of the electron pairs across the short dimension of the rod. Then it has this long tail out to long distances, which correspond to these electron pairs along the long dimension of the rod. Disks actually don't look that dissimilar from spheres. They're just kind of more flat. They have a wider distribution of the electron pairs. The peak is earlier. Hollow spheres are kind of the opposite of the rod. You have, some short distances in here, but you have a lot of longer distances across, here and across all the way across the center of the sphere. So it peaks near the maximum dimension, near this outer shell distance, basically. And then, in some ways, most interesting is actually the case of the dumbbell, where we have 2 separate spheres separated by some thin domain. And so you have this first peak, which corresponds to all the distances between, or rather within a single domain. So within these 2 domains, they all show up in here. And then you have a second peak, which corresponds to all the different distances between the 2 domains. So you can see here, the second peak is everything across this. And so this is actually very representative, exaggerated perhaps, but representative of what multi-domain proteins, especially if they're separated by some kind of flexible linker, might show up as in the P of R function. And to put some actual data on it, globular proteins, you can see is this blue one here, look very much like the sphere, usually a little bit of a tail here. Multi-domain proteins end up with these shoulders corresponding to distances between different domains. And then unfolded proteins actually kind of crunch in at the beginning and then have these long extended tails. And we'll talk about that again a bit on Friday. And we'll talk more about flexible systems. And so the shape of this function is very useful in even just getting an initial idea of what you're looking at for your sample. The P of R function, however, can provide more than that, though. So it provides this maximum dimension. But you can also use it to get out the RG value of the curve and the I of 0 value. So at the very least, this is useful for cross-checking your Guinier analysis. Are you getting the same thing? If you are, then you've probably done a good job with both, or I guess an equally bad job with both, potentially, but hopefully a good job with both. But there are advantages. It uses the entire curve, and so especially for large particles where you might have a small Guinier range, not a lot of points, or where you have noisy data, being able to incorporate all of the information that you've measured to calculate these values can make it a more accurate determination. So these are the ways that the P of R function is useful. The other way that it's useful is often, particularly the maximum dimension, is used to constrain the search space when you're doing like ab initio reconstructions, which we'll talk about on Thursday. And so it's necessary for plugging into a number of these kind of more advanced techniques. But even without doing that, it provides some initial kind of shape information about your protein in real space. So it can be quite useful that way. So that's what it can tell you. What I want to talk about now is how we calculate it. So when I started this section, I said we were going to be talking about indirect Fourier transforms. And the question that might come up naively, certainly when I was learning about it, is why can't you just do an actual Fourier transform? And there are several reasons. One of them is that you have, again, this kind of pesky infinity hanging out in this integral. And we never measure data I to infinity. The other is that you have measurement noise. And so this finite extent of our measurement and the measurement noise means that if you do a direct Fourier transform on your scattering profile, it distorts the true P of R function. You get what are called truncation artifacts showing up, which usually manifest as kind of high frequency oscillations in the profile. Instead, we actually go about this kind of backwards. Instead of taking IFQ and calculating P of R, what we'll do is we'll use this version of the equation. We'll pick a maximum dimension. We'll find, using this equation, we'll find a P of R function such that with that maximum dimension, the P of R function that best fits the scattering profile. And then we'll check to see if that P of R function makes sense. So it's really this backward approach where we generate the P of R function given a maximum dimension by fitting against the data. And that's why we end up calling this indirect Fourier transform. The other reason it is that typically we include criteria beyond the fit, which like the chi-squared value. So you include what we call regularization parameters. And so these add in extra information that the Fourier transform doesn't know, but that we do. So you might impose conditions like saying, it's more likely that the P of R function tends to be smoothly varying. We don't expect high frequency oscillations in the number of electrons. You can impose conditions on saying the P of R function should be positive, which is true except in the case of protein detergent complexes, for example. Things like this. So you can make these additional constraints to improve the resulting value and get something much better than what the direct transform would give you. Again, we'll do this in the tutorials tomorrow, but the most common way that we do this is we use a program called Genome to do the IFT. And again, this requires this estimate of the maximum dimension. So once we've estimated the maximum dimension, we generate a P of R function. We then have to judge, have I picked a good maximum dimension for my system? Is this the right value? And so this is really where the key of generating the P of R function comes in, is I've picked a D max, I've calculated the P of R function. Is this the right D max to have picked? And there's a set of criteria that we use to judge this. So first, and perhaps most importantly, we ask, does the P of R function fall gradually to zero at D max? The idea here is that proteins, macromolecules, they don't have sharp edges, right? Usually there's some amount of flexibility, even if it's minor. They have side chains that are hanging out in solution wiggling. Maybe you have an NRC terminus tail that has a few flexible residues on it. Whatever it is, you don't expect there to be an abrupt cutoff to your protein. Instead, what you expect is this kind of smooth, gentle approach down where you have these, last little wiggly bits that are kind of tailing out as you go to the maximum dimension. And so if you underestimate the maximum dimension, it tends to be artificially forced down to zero abruptly. If you overestimate it and your data set's good, you'll see that this will stay near zero and often oscillate about it. I'll show those on the next slide. So we sometimes describe this as you want the end of your P of R function to kind of look like how you want your airplane to land, right? You want your airplane kind of come down and smoothly touch down on the runway and just kind of gently, touch down and slide along the surface. You don't want your airplane to nosedive down onto the runway. You don't want your airplane to come down and bounce along the runway for a long ways. So if that helps you think about it, right, you want this nice, smooth, gentle approach to Dmax, just like the airplane. So that's kind of the most important criteria for judging Dmax. There are some additional ones, though. So the first P of R function should go to zero at R of zero and R of D max. Often that's enforced by the program you're using, but you can sometimes turn off that forcing and verify it's true. You want the transformation of the P of R function back into this space here to make sure that the fit to the data is good. Again, you want these fit residuals to be mostly flat and randomly distributed. It's usually true that the RG and I of zero from the Guinier and P of R will agree well. This is true except for flexible systems, which again we'll talk about on Friday. You want the fit criteria to be good, so you want this chi-squared or total estimate or something like that to be good numbers. Good chi-squareds are usually near 1, for example. Your P of R function should always be positive, except in proteins in a lipid system where you may have a negative peak at the lower values that corresponds to the detergent, the lipid. And that's because we're looking at an electron density difference, and lipids have electron densities lower than that of the buffer. And so you end up with negative electron density as seen by your difference scattering. The other thing I want to point out is that because there is this kind of estimation of what looks good in these criteria that we have, even for good data, determining the maximum dimension is often only accurate maybe 10% at best. So if you told me, I measured my system in 2 different conditions and I got a maximum dimension of 100 and 101, I'd tell you that's not different. There's no change there. There's no reliable change. If you told me it was 100 and 120, yeah, that's something that I believe. The other thing is, of course, you can have the same maximum dimension and change shape, and that's also meaningful. So that may be a better way of looking at it. So a little bit more on these kind of judging criteria, right? So here's the same protein where I've calculated the maximum dimension at 83, 103, and 123 angstroms. And what you'll see is for 103, it comes down kind of nice, smoothly to 0. For 83, it's forced down to 0 very sharply. And for 123, it comes down and it stays about 0 and oscillates about 0. So this is kind of what you want to look for when you're judging a good maximum dimension. My usual approach to this is kind of the generic formula for finding Dmax from good quality data. This is using the genome program in RAW, which is what we're going to do in this tutorial tomorrow. And this tutorial will walk you through this. You open the genome interface, it'll automatically try to find a reasonable Dmax. I then set the value to kind of 2 or 3 times that. I look for where the function's dropping naturally to 0. I set the Dmax value to that. I turn off the forced 0 condition, and I tweak the maximum dimension up and down until the P of R function's coming to 0 with the force turned off. Then turn the force back on. If you have good quality data, this ought to produce a good P of R function and consistent Dmaxes pretty much every time. So this is a kind of generic approach, and we'll go over this tomorrow in the tutorials. So all that being said, now we can look at this plot I was showing on the very first slide of this section and maybe understand a little bit more about what's going on. So here we have our data. Here we have the pair distance distribution function. You can see there's multiple peaks, so there's some kind of interesting shape going on here. This is actually what a ring looks like, this polymerase ring. Here we have the transform back to the data. You can see it fits quite well. And so this is a nice smooth approach to 0 at Dmax. This is a good P of R function. This is what you would hope it would look like. So in addition to all this information, P of R function is also sensitive to problems with your data set. So one thing that you'll see if you have aggregates in your sample is it'll be very hard to find a reasonable Dmax, especially if you have significant aggregation. Here I'm showing a case with kind of extreme aggregation, where you can just keep extending out the maximum dimension, and it's still being forced even when you force it to 0 out here. Whereas the same protein, shown in red without any aggregate, has a nice smooth approach to 0 near 100. And so aggregate typically shows up as this kind of long extended tail and trouble finding a maximum dimension for your particle. So that's one thing to be aware of. Interparticle interference that leads to downturns at low Q, this repulsion, this leads to an artificially small Dmax. And this can be a little bit more subtle, right? Because you don't necessarily know what maximum dimension you're expecting. Here I'm showing the same protein at different concentrations. We have this concentration effect showing up, and you can see the shape of the P of R function actually looks good, but the maximum dimension has been brought in. And so the key here is if you extend out that P of R function past the maximum dimension, something that has a repulsive effect is going to drop below 0 out here. Whereas something that is good, something that doesn't show these effects, will stay near 0. You can see that as I've extended both of them out to 50. This one has this very clear dip, and this one does not. So that's another thing that you can look for. So to summarize about the P of R function then, it provides real space structural information about the shape of the macromolecule, provides an estimate of the maximum dimension, potentially more accurate determination of RG and R0. It's sensitive to aggregation and interparticle interference. It's generally required before moving into more advanced analysis. And so this is a very useful, again, model-independent way of getting out information, real space information on the shape of the macromolecule. I have a couple of summary slides, so I'm just going to go through there, and then we'll go into the Q&A, and I can take any questions on IFTs then. So to provide a summary of data validation, this is the same plot that Kushal, or plot set that Kushal showed at the end of his talk. It's from this very nice 2010 review by Jacques and Trivella. And so it has three columns. There's what good data looks like, what interparticle interference looks like, and what aggregation looks like. And now you should be able to recognize kind of what this is showing, right? Good data has a nice linear Guinier range, has a well-defined P of R function that drops smoothly to 0. And if you extend out the Dmax, that P of R function stays near 0. Interparticle interference shows downturns in the profile. The RG value goes down. You can see these curvature in the maximum dimension. The Dmax is artificially small in the P of R function. And the P of R function, if you extend it out, goes negative at larger R values. Whereas for aggregation, you see these upturns at low Q that can be reflected in upturns or steeper slopes in the Guinier region, larger RG values. Dmax tends to be longer, and you can have trouble finding good maximum dimensions, even if you extend it out. And you can see that also down here, where particularly for the larger amounts aggregate, the Dmax value just kind of keeps going. And so this is, I think, a good little summary plot of a lot of the effects that we just talked about, how they affect both the Guinier and the P of R function. So it's a useful reference for you to come back to. Just to summarize then the data validation, the Guinier fit will show most of the issues. P of R function will help you catch aggregation and interparticle interference. Molecular weight is used to validate what you have in solution. You want to pick the appropriate method for your system. The Kratky plot's sensitive to background subtraction. Dimensionless Kratky sensitive to Guinier fit. Usually we don't use it as a validation technique. But if you see something weird there, it may be telling you about one of these things. In terms of the data analysis, the Guinier fit and plot will give you estimates of the RG and Y0, sensitive to data quality issues. Molecular weight's relatively unreliable, but again, you have to use it to validate what's in solution. Kratky and dimensionless Kratky plots provide analysis of flexibility and shape. The P of R function provides real space shape information, estimates of the maximum dimension, and a potentially more accurate determination of RG and Y0. And the P of R usually is required before we advance on to various other analysis techniques. And so with that, I'm going to stop my slide share. I've done a lot of talking. We'll go into a general Q&A.